Okay, let's make a start. If not, we'll never go home. All right, sit down, please. Okay. All right, listen. Okay. Let's start. All right. So last week, not last week. This week we talked about lamina. So we're doing external flow. We talked about lamina boundary layer and turbulent boundary layer. All right. Today we'll talk about flow around external bodies. All right, not just the boundary layer, but the overall one. All right, and flow separation. You all did the lab, isn't it? You saw that the flow separated, isn't it? So now we want to discuss why that happens. Okay, and all this leads to basically relate to drag. All right. Lift not so much. This unit we don't talk so much about lift. Okay, but the drag forces. All right. Okay, so I've typed in turbulence and this is what I get on Google. Okay, got funny things and all that. Okay, so this one. Okay, let's not look at the funny things. Okay, so basically, laminar flow is like layers, like laminate board. The flow in layers. Okay, if there's a bit of unsteadiness, normally it's associated with one length scale, one size of a few sizes, not big one, not a big range of sizes. All right, but when your Reynolds number gets high, all right, what tends to happen is your viscous forces cannot damp out all the disturbances, so the disturbances propagate and grow. So as long as there's something driving the flow, something driving the upstream thing, maybe the car moving or the flow, waterfall falling from a waterfall or something is driving the flow. All right, the flow will tend to break up and into turbulence, and the turbulence is a process where the energy is dissipated. Okay, all right. Turbulence dissipates energy by spreading it out and all right, mixing the slow moving fluid, the fast moving fluid, and so on, and that through that dissipation happens, and that finally the flow structures break up into fine enough that they the flow structures break up finally until they are very small, and when the vortices are very small, they get dissipated by the viscosity and go to heat. Okay, so if you still not clear what it is, so this Leonardo da Vinci. Okay, he draw this picture. That time he didn't understand what turbulence is, but he draw it really had some idea that flow at different scales, big, small, and so on. In modern day one picture look like this, big, small, and a mixture of them. Alright, and all in the same direction. This only a slice of it. Some of them will be swirling this way, and this way, and this way, and so on, and this way. Okay, so it's in all different directions. Turbulence must have that three-dimensional part of it. Okay, if you see a picture like this, all right, so these are simulations, you get a lot of this, okay, so you get a lot of disturbance, all right. So if you see smoke rising up like this, that one turbulent. I thought there was a picture not so turbulent, maybe down here. Here. So this one actually not so turbulent. All right. You don't see that big scale. This one is just smoke rising. I think there's a cigarette here. All right. Okay. A cigarette or some smoke source. The smoke rising and swirling up. Here, this part quite laminar. Here maybe turbulence just starting to happen. Okay. So this one is low Reynolds number case. All right. You can see very different. The turbulent case, where is it further down? I thought I saw just now. Oh, the picture that I used also. Okay, this one is a clearer picture than the one that that I showed last week. No, last week on Tuesday. Okay, this one you can see. All right, I think again another smoke source or dye source. Okay, as it comes out, it got some big structures here. It got some very fine structures there. That's turbulence. Okay. So if you like to watch those old movies, those Japanese ones, I don't know, they like to have men dress up in a suit like Godzilla or Ultraman, all right, and then they run around, okay, and then they shrink the environment down, all right, so that the man in the suit looks like he's the giant. Okay, they don't do that anymore these days. Okay, that one looks, I guess, looks a bit obsolete if you do that way, but you can. All right. After all, children wouldn't know any better. Okay, but what happens in those movies, all right, is sometimes they got volcano or they got features where the smoke or the water comes out. All right. Okay, so so the Reynolds number is rho, Vd, or mu, okay, or L. All right. So in those cases, because they shrink everything down, the L is a lot smaller. All right, model. All right, okay. The L is a lot smaller than outside in the environment. So if they had like a volcano or anything like that, if they do it that way, then what you notice is first of all it's quite fake because among other things, all right, you see if there's a volcano in there, say, or something, let's say volcano, the real volcano that you see outside will look like this, okay, because the real one, the L is big, okay or not? And therefore your RE is high, and therefore you get turbulent flow. So you would see all the different scales. All right, but in the man in the Ultraman suit running around in the small environment, the L tend to be low. So this one turbulent. All right, not very turbulent. Say laminar or transition. All right. So what you tend to see in those movies is you get to see the smoke coming out. Hey, where was that picture? Something like this. Okay, now. So, therefore, these days, I guess you play a lot of computer games, right? All right. So they take a lot of effort to try to make the surrounding, the water, the smoke, and so on to be realistic. So therefore, they need to spend a lot of time to make sure that the flow actually looks turbulent and not this one. Okay, this one okay if you are really playing with very small characters or in load, right? But if you are anything realistic or big, then by right, the flow should be quite turbulent. All right, so that's one way to, okay, and that's why the situation is different. All right, earlier we were talking about modeling. All right, to model to be a correctly model everything, you by right the Reynolds number should be the same. If not, you won't get the same result. Okay, so just by scaling everything down, all right, it's not actually an accurate model. The man in the Ultraman suit running around, supposedly 30 stories high, all right, it's not an accurate model of if the real thing was 30. So you cannot do measurements on that man in the running on the model environment. It's not fully represent the big one. Okay. All right. Any questions there? All right. If you want to watch Ultraman and all that, YouTube got a lot. Okay. My son watches a lot. But he's 3 years old, so to him it's just it's real. Okay. Later on, he might realize that something's wrong here. Okay. All right. Okay. So all right. Okay, so just to recap, laminar flow, layers like that. All right, laminar boundary layer, turbulent boundary layer. Okay, the mechanism here, Re is low, mu dominates. Okay, here Re is high, the rho VL dominates. Okay, so anytime you get a little bit of disturbance, so we have the whatever the mean flow driving the system, okay, to get this one, right? So the energy is coming from the mean flow, U infinity is driving the system, all right? In this case, all right, there is a lot of deviance, big and small, the turbulence, all right? So the turbulence makes us, what the effect of turbulence is, it breaks down your layers. Okay, so fast moving fluid moves up, slow moving fluid moves down, mix, you get a very linear velocity profile. Okay? Well, you get a very linear and a very sharp one at the end. Okay? Alright, so that's our discussion so far. Alright? Okay? You want to do example? Because you got all these equations here. All these equations here. I got bird also. Okay, our equations here. So, laminar. Alright. Laminar, we got one set of equations. Alright. Alright, I hope you remember del star is around 0.33 to 0.36 del. Alright. Okay, what are the other equations? Del on x is equal to 5 over square root of Rex. Okay, so it's testing my memory. 5 over. Alright, and I think the other one is what? CD. CDF is approximately, don't need copy down as in your notes. 1.31 over square root of Rex. Is that correct? Is that what we used last time? Okay. All right. So that's for the laminar flow. For turbulent flow, okay, del star is approximately del on 8. Is that correct? Okay. Del on x is approximately what? 0.37. 0.37 on square root RE to the 1 on 5. It's a lot thinner. Okay? And CDF, this for smooth plate. Smooth plate. Alright? 0.07 to the RE 105 also. Okay? So, alright, want to do an example. Let's do a turbulent one. We did a laminar one. Okay, let's say for air, rho is 1.23, mu is, what is mu? Something 1 times 10 to the minus 5, is it? Huh? No, I don't think it's 1.2. 1.8 by 10 to minus 5. Okay? Let's just use those numbers. Alright? So let's say the flow moves at air at 20 meters per second. Okay? We assume the RE transition is, what's the transition? 500,000, is it? 5 by 10 to the 5. Okay? But it can be go as low as 2, can go up to 3 million or so. Can be low as 200,000, 100,000, up to 3 million. Is that correct? Yeah? You don't memorize these things, Okay, RE 5 by 10 to the 5. Okay. Alright. So, step 1. Alright, question. Determine. So, this is X. Location of transition. Alright. So, REX is equal to rho Vx over mu, and that is equal to, say, 500,000. Alright. So, in this case, rho is 1.23. Velocity, what is the velocity? 20 meters per second. Alright, that's about 60, 70 kilometers an hour. X over mu, 1.8 by 10 to the minus 5 is equal to 500,000. Okay, what is X? Someone punch into the calculator in meters. So, at X, alright, the X we find here, laminar, more or less, here, turbulent. That's a transition. More or less. Alright, there'll be a gap in between there, where there's actually a transition range. But never mind. Let's keep our life simple. Just call that laminar, call it turbulent. Alright, but there's, in fact, if you see the picture, alright, where's the picture? If you see the picture, there is a transition one. See? Here, laminar, there's some transition, and then it goes to turbulence one. Right? Yeah. Right. Unless otherwise told. What's the answer? 0.366 meters. Okay? only a very small part of the plate. All right, because I didn't tell you, but let's say L is 10 meters. Oh no, 10 meters. Let's say 5 meters. Okay, 5 meter long plate. Nice big Reynolds number. Okay. All right. So for in this case, all right, there's an initial laminar part. All right, but if your plate is a lot longer than the 5 meters, than this transition, we can more or less assume, all right, for simplicity, all right, we assume that it's turbulent. All right, assume, all right, L much larger than X transition, much larger. All right, we assume turbulent boundary layer. Okay, so find the del at L equals to, find del star and CDF of plate. All right, assuming smooth plate. Okay, so in this case, okay, del over X is, well, first we can calculate what the REL is. REL is equal to rho 1.23 times 20 times 5 over 1.8 by 10 to the minus 5. What answer is that? All right. Then del on X is equal to, what's the number? 0.37. 0.37 over RE to the 1 on 5. Del equals what? And yeah, X is 5 at plate of plate. Here I forgot to put at X equals to 5 meters. So at the end of the plate, what's the boundary layer thickness? All right. Del star is equal to del over 8 equals to what? CDF is equal to F drag over half rho G squared A. All right, and that is equal to 0 point over RE to the 1 on 5. What is that? 0.07. All right. So the velocity is equal to, rho is equal to 1.23. The velocity is equal to 20 meters per second. Area is equal to 5 meters by, let's make the depth into the page 1 meter. 1 meter. All right. So what is the F drag? Okay. All right. So analysis. All right. Once you identify turbulent flow, just apply the equations. These are lines of visible feet. Okay. Okay. What's the Reynolds number? 6.83 times 10 to the 6. What is del? 0.08 meters. So it's 8 cm. So even after 5 meters of going around the plate, the boundary layer is only 8 cm. Okay? 8 cm, about like that, huh? Alright, so it's still very thin. So del over 8, very easy, 1 cm. What is the drag force? What's the drag force? Anyone? Still calculating. 0.7 newtons. All right. You can see for such a big plate, 5 meters square in 20. Only one side. You want two sides, then you multiply like 2. All right. But for such a big plate, 5 meters. All right, moving quite fast. 70 kilometers an hour. 20 meters per second, about 70 kilometers an hour. The drag is only so small. All right. So in air, in water, will give it like this, but never mind for air. So even in laminar flow or turbulent flow, the skin, all right, the skin friction drag is small. Okay, no? All right. So what I'm saying, laminar flow, skin friction, drag small. Is very small. Turbulent flow, skin friction drag is not very small, but small. Okay? All right? So turbulent is small, laminar is even smaller, so very small. Okay? Just to give you an idea of the scale. All right? Here we use the equation to calculate, but by right, there is this picture here. Okay? Your that equation by right is this turbulent line or smooth plate. If your plate is rougher, you will depending on your Reynolds number and the roughness of the plate, you can look up from this graph here. Alright, but normally for this one you don't really look up this graph for this unit. Alright, but we'll look up a similar graph for pipe flow. Pipe flow, you definitely need to consider Reynolds number and surface roughness when we're calculating the pressure losses of the drag on the pipe flow. But that we'll do next week. Okay? Remind me to tell you next week, Monday holiday, and Tuesday the lecture postponed to Thursday. But I'll talk to you about that later. Just remind me that one. Thursday what time? 6 to 7. Yeah. So yeah, remind me to tell that at the end of lecture. Okay? Alright, so next week we do pipe flow and we need to worry about that, but this one normally we don't need to worry about the roughness. Okay? Alright, so from here on let's talk about the story now. Alright? You seen? Okay? Let's say for a streamline shape, okay, then the flow just goes round. It has the boundary layer here and the boundary layer on the bottom side. Okay? So we expect the drag due to skin friction. Okay? Drag due to skin, or drag dominated by alright. But if your one not streamlined, like the flow visualization we did, did you see like that? Okay, when I put the cylinder like that, you see like that. Okay, I presume you didn't. What you saw was the flow separate. Okay, so today, the last remaining of today, I'll try to finish by 6, but not a little bit after. Okay? Alright, compensate you guys for all the missed classes, which I haven't replaced yet. Okay? So at some point, you will separate. Alright? The separation mechanism I'll talk about next. Okay, why it separates. It will come soon. But basically, alright, it separates, and when it separates, what you have here is a very low pressure. Alright? What we have here, because the flow is forced, the flow is coming along, and it's forced to get out of the way. Okay, no? So actually, this thing will generate a very high pressure here to push the flow out of the way. Okay, no? In fact, remember I said there's an unlucky fella that will go and stop here. All right. So the pressure on the front side is high. Okay, no? All right. The pressure on the front side is high enough to stop this fella. All right. So the pressure, the force is high enough to stop bring this fella to a stop. All right, and high enough to push the flow out. Okay, no, to change the direction of the flow. So you have high pressure in front here. Okay. All right. So for a block body, like a cylinder, a square, a building, anything else, yourself, okay, standing outside in the wind, will look something like this, more or less, okay. So you feel high pressure at the front and a low pressure at the back. Okay? Alright? So this will result in high, alright, large drag due to what? Due to, sometimes they call it pressure drag. Well, obvious. Sometimes they call it form drag. Okay? So block bodies, alright? Okay, streamline one. Alright, if you want to reduce the drag on here, it can be more streamlined. If you want to reduce the drag on there, it's more difficult. Alright? Either try to make the boundary layer laminar or try to use other mechanisms to do that. Okay? But we don't have to talk about. Alright? Okay so far? Alright? So, normally, we calculated it before. I think in the lecture slide also got. No need this one anymore. This one no need. Okay. So you can see here, this is the drag coefficient. This is the one. Alright. See the drag coefficient very high. Very high, no? Quite high. Anyone low one or not? No. Okay. All right. So drag coefficient very high. If you want on, just now your CGF was all very small. Here all the numbers all like 1, 2, and so on. Okay. These are all very very large objects are here. Obviously get separation and so on. All right. So from that, if you were to calculate, give a typical size. Let's say. Let's take that one. Okay. See here they got such a simple one. Okay. Let's say dolphin very small, huh? Dolphin streamline. Okay. So streamline one, less separation, you get like this. But it's quite high because he needs a lot of flight thing. Let's say take a tree A tree at 20 meters per second, the drag coefficient say 0.26. Okay? So, no, that's also quite small. Let's take a big one. Take this one. Okay? Drag coefficient 2.3. Alright? So assume in this case, same like our problem, the area, let's take 5 by 1 or so. Okay? 5 meters this way, 1 meter to the pitch. Or 1 meter this way, 5 meters to the pitch. Doesn't matter. Okay? So assuming, alright, how do I get out here? Okay, escape. Alright? So let's say for a typical geometry, what's it like this? All right, area equals 5 by 1. Drag coefficient CD is 2.3. All right, let's look at the force generated, just for argument's sake, just to show that it's a very big number. All right, CD is equal to 2.3 is equal to F drag over half rho G squared A. It's equal to F drag. Same problem like just now, half 1.23 G squared 20 squared area 5. All right. Not quite easy, not quite fair to compare because the other one was a 5 meter stream, 5 meter square streamline. This one of 5 meter square is actually facing the flow. All right. 5 is very blunt. Okay. What number you get? All right. You get 2,829. All right. Okay. So, okay, the other one is 3.6 meters. This one is 2,000 meters. All right. Okay, so that demonstrates the difference in magnitude we are talking about. All right. Is it okay? Why are you so excited? It's good to know that some people are excited. I hope all of you are. This is a very exciting material. Okay. All right. So now we might ask why. Why does flow separate? Okay. So in that case, we need to draw. I'll draw like the one in the thing so that we're not so far. But actually, I can draw it in reverse also. Okay. All right. Which one you prefer? Maybe I draw reverse. Okay. So this is, let's say, this is the top one streamline going straight. This is a cylinder. Okay. So this part here is solid. All right. So initially your boundary layer is here. Okay. My picture is the upside down of the one used in the textbook or the one in the lecture notes. Okay. But both tell the same story. All right. So there are two regions here. Okay. So maybe this cylinder is a bit flat on the top. So we got three regions here. All right. This region, what is happening to the velocity? Velocity, as you go from here to here, to here, what's happening to velocity? Increasing. So what's happening to pressure? Bernoulli equation. Velocity go up, pressure go down. Okay. So can I, let's say this is the x direction. Can I say dp on dx equals to, all right, actually this is it correct? Velocity going up, pressure go down. All right, dp dx is negative, pressure dropping. All right, this I'll call it favorable pressure gradient. Favorable pressure gradient. Okay now. Why favorable? I'll tell you later. Okay. All right. So then it goes to a flat part. What happens here? V about constant, so P constant. Nothing much happens here, Okay. It just goes in. Okay. And then it comes out here. V. What happens here? As you go down this way, V down, isn't it? Okay, now this is for incompressible flow, low speed flow. All right. High speed flow, the physics change a bit, so we won't talk about that now. All right. Low speed flow, if you go to bigger area, what happens to the velocity? Velocity go down, okay? Okay now. Pressure go up. Alright, dP on dx equals to positive. We call this unfavorable. Okay, so the favorable pressure gradient, what happens to the velocity here? Velocity also increases, isn't it? Alright, so we have, let's say we have the boundary layer coming along. Alright, so the boundary layer later on here would be general, there will be a general increase everywhere lah. Okay or not? Alright, because the velocity increase, you expect everywhere to increase. Okay or not? Alright, so we have the boundary layer coming along, the boundary layer speeds up. Those that slow one gets a bit faster, those faster get even faster. Okay, everything will speed up through the whole. Okay or not? So actually we expect here, we expect our del, our boundary layer thickness to go down in this region. Okay? It actually comes the inner boundary layer because everything's speeding up. Okay? So not only your U infinity go up, but the location where you reach U infinity also faster. Okay? Here nothing much happens here. Okay? What happens here? The velocity slow down, isn't it? Okay, slow back down. Okay. Could it go to the real extreme case where the velocity goes into reverse? Okay. So in this region, velocity slowing down. Okay. So you will get a situation where the velocity will slow down that much, then will go into reverse. This is called an unfavorable pressure gradient. Okay. Alright? Unfavorable because of separation occurs. So normally they don't call it velocity going up, velocity going down, or that. So maybe that sounds like kindergarten. They call this favorable pressure gradient and unfavorable pressure gradient. Where your velocity slow down until the point where what happens? Your velocity slow down until the point where flow reversal happens. Okay, so that this line is called a separator. So this point where it initially starts to go into reverse, that's called the separation point. Okay, that's your separation point. Flow goes into reverse, and there. So there I call this the shear. This one, this is still called boundary layer. This one called shear layer, called separator shear. Can't call it boundary layer because not boundary anymore. So this one is called the shear layer. This one equals separated shear layer. Okay. Now the explanation in the notes is upside down. The boundary layer is actually going along the top surface here, but the story is the same. Okay, I drew it here because it's very clear. You see the cylinder. You see suddenly the flow separate. You see that? I didn't trick you, right? So you alright photo also, right? So the evidence is clear. You saw that, and that's what happens. Okay, but the note had this thing on the top and the wall on the bottom, and it showed the same thing happening on the top wall. Okay, that's undergoes that one. That's the same. Why is the velocity increasing here? Because the channel which is from here to here, the channel from here to here is getting smaller. All right. Okay. M dot is equal to rho AV. So your A go down. M dot the same M dot going through here. The V must go up. All right. Assuming your rho constant. Okay. Now that's what's happening here. Opposite on the other side. Okay. All right. So final point. All right. Actually, two things out. Final point and then the application. Okay. So you recall laminar boundary layer like this. Okay. Turbulent boundary layer like this. Okay. So assume these two go through that process. Alright. Here you got a lot of very slow moving fluid, very thick boundary layer. Here you got very fast moving fluid, very thin boundary layer. Which one you expect to separate first? Alright. Laminar, turbulent. Okay, you go through this process. I know. This one, if you slow down a little bit, what happens? Goes down already. This one, if you slow down a bit, still okay, right? Okay, because here got very fast moving fluid, get a wall. Slow down a bit, it's still going forward, still haven't goes down yet. Okay, no? This one goes down reverse. This one reverse yet. Okay, no? Alright? The front set it. Alright? So this one, if you slow down a little bit, it will go into reverse. It will separate first. Alright? So, number one, alright, this will separation will only happen in an unfavorable pressure gradient. Okay now? Alright, number one. Number two, turbulent flow more resilient to separation. Turbulent flow more resilient to separation. Okay? So, alright, if you are, okay, so if you want to, so if, right, you copy down, finish now. Alright, let me copy first. Alright, so if you, where did we, okay, if you are in this case, okay, alright, for block bodies, you will want to delay separation. Okay or not? Alright, for bluff bodies. Alright, you want to delay separation. Okay? Why? Because if you delay separation, you got narrow wake. Alright, delay. As versus no delay. Right? Okay or not? So, why? Because the drag force, well, the front side is the same in both cases, more or less. Alright? But the back side, here, the drag force, drag is approximately P on the front times A on the front plus, well, actually it's minus, but the back pressure is actually minus. Alright? Alright? Minus P at the back times A at the back. Okay? Alright? So the P at the back is like this one, this P. Right. This P is negative, so this is less than 0. It's a suction. Okay? It's below atmospheric. Alright? So what you want to do, we can't do much about the front will be in front. Alright? But for the back, we want to, number one, reduce this area by delaying separation. You have a narrow wake. Alright, the pressure is most negative in the wake region. If you can narrow that wake region, alright, we can reduce the drag. Alright, not? Bluff means not the opposite of aerodynamic. Okay, the word bluff means the opposite of aerodynamic. Okay, like not aerodynamic. Alright. Okay. Okay, you want the pressure at the back to be alright. So to reduce that, you want, okay, reduce that. you want the A to go down, or that, and this A at the back. It is not necessarily the whole area at the back, but the A of the wake. Alright? Alright? More the wake. Okay? No, it's not really this. The area of the back is always the area of the back. You cannot change that. But where the pressure is most negative is the area in this. Alright? In this region, the pressure is very negative. Okay, not? Alright? In this region, the pressure is very negative. So you want to decrease that region. So to reduce drag, you want to delay separation. Okay? Is that alright? Then you reduce the area of the wake. So not really, we're not reducing the area of the back, but the area of the wake is reduced. The wake area, this one, this region, wake with very negative P. Is that okay? Alright, so the pressure in the wake is very negative. It's very law of suction. Okay? Alright? And we do that. So far, you follow the story so far? Story very exciting, huh? I think at the back there. Alright? So, yeah, very negative. P is the pressure. Alright? So, in the wake region, the pressure is very low. Law of suction. So, number one, you want to reduce, if you want to reduce drag, you need to delay separation. Alright? Huh? W-A-K-E, wait. Huh? Is that alright so far? Okay. So, and also, delaying separation will result in more pressure recovery. Wow, this is powerful words, huh? Okay, what that means, I'll show you later. What that means is, when you have a narrow wake, when you delay separation, not only the area reduced, but the pressure is still negative, but be less negative. Alright? Alright, delayed separation will more pressure recovery, means the pressure will initially go negative. Alright, more pressure recovery means it doesn't go so much negative. Alright, below atmospheric. Negative pressure, in this case, all the pressure is relative to atmosphere. So positive pressure is pressure higher than atmosphere, negative pressure is pressure below atmosphere. Okay? Alright, so far? So to show the story, okay, I think there's a picture here. Here. Alright? This is the story. Alright, boundary layer. If you have a laminar boundary layer, alright, laminar boundary layer very prone to separation. So it separates very early. Laminar boundary layer separates point C separately, 90 degrees. Alright, so it separates here, and the pressure in the wake very negative. Right, this negative, negative 1. Okay, now, right? Turbulent one is separate a bit later. When it's separate, huh? Okay, it separates about that point there. Alright? So, laminar one separates here. Turbulent one separate later, separate maybe 90, 100, 110 degrees like that. Alright? And more recovery. You can see the pressure recovers and more recover. It won't recover all the way, but does that make sense so far? Alright? Laminar one, as I said, the pressure, the velocity profile is more unstable, very slow moving fluid near the wall. As soon as it slow down a little bit, it will separate. Okay? For turbulent one, it needs to slow down quite a lot before it separates. Okay. Alright, so it separates later. When it separates later, the pressure will cover more. So let's see the pressure is going up. So it go up more before it. And this is the pressure and the weight. For the laminar one, this is the weight basically from here all the way here. Alright. Okay, the laminar one, the pressure, the weight is this big area from 90 all the way to 180 degrees. Alright, 90 to 180 degrees for half side. And the pressure is at -1. Pressure coefficient. Here, the weight is narrower because it's separate later, more pressure recovery. The pressure is only -0.5, so the less suction over a smaller area. Okay, now. Alright, so this story now very complicated. If it's a streamlined body, then obviously the laminar boundary layer is better than the turbulence boundary layer. Right? Laminar boundary layer, that's right. Alright? Okay, so I have to write here. If not, you all cannot follow. Okay? No, I cannot write here. Right here, hang on. That's Microsoft. But I'm sure Microsoft 2013 is better. I'll get Windows 8 and 2013 next year. But at the moment, yeah, cannot write there. Okay. What did I say? What? What did I say? Okay, streamline body. Okay, then obviously laminar boundary layer better, less drag. Okay, but bluff body, all right, turbulent buoyant BL, although you expect the skin friction to increase, but that's negligible. All right, yeah. Turbulent boundary, delay separation, more pressure recovery in wake. Okay, so number one, delay separation. Number two, more pressure recovery in the wake. All right, so what result then? So overall, less pressure drag, and overall this is good because pressure drag is much larger than skin friction. You follow the story so far now? Okay. Alright. So you compromise. The turbulent boundary layer, yes, the skin friction drag will increase. But you delay separation and you get more pressure recovery, so you have less pressure drag. And that pressure drag is many times bigger than your skin friction drag. So it's worth the compromise. Okay now? Alright? Okay? So this leads to, well, I'll let you finish the story. Anyone got any question about the story now? Alright? And then that character kill that the other character with the candlestick. Okay. So the final one. Wait first, don't panic. Okay. So, if any of you play this example here, if any of you play golf, all right, you know why the golf ball not smooth. All right, the golf ball boundary layer is at the transition stage. All right, when you hit it very hard, okay. When you hit the golf ball very hard, the boundary layer of the golf ball quite small. So it's at the maybe 20,000, 50,000 stage. Okay, so if you have a smooth golf ball, actually your drag will be higher than if you had a golf ball with dimples. Alright? Here. Okay? Say application here. So if you're at the transition to turbulence stage, it's very good to instigate the turbulence to reduce the drag. Alright? Have you seen another application is, have you seen a car? Some car out there they modify one, They modify with big wheels and big exhaust, but that's not what I want to talk about. All right. At the just before the roof, just before it goes down the the glass, there are like little fins sticking out. What's it called? Roof scoop. You seen before? All right. How do you get this? Okay, let's try type his word here. What do you call that? Correct now, after all sorts of funny pictures come out. What's it? Okay. So again, this one, and sometimes on aeroplane wings, not the big aeroplane, a big aeroplane around not big enough. On small aeroplanes like the private one, that can crash aeroplane. Okay. On the wings or on the roof, you see this one. This has the same, are there for the same purpose. Here the flow like laminar, you instigate it, you have turbulence, narrow weight, reduce drag. Alright. Okay. So I think that's about it for this lecture. So finally, one announcement I forgot to say earlier. So next Monday holiday. Alright. Next Tuesday, what happening here? Next Tuesday, the 10 to 11 lecture are not free. So that class is rescheduled to Thursday, 5 to 7. So we move it there. Is that okay for everybody? All right. I'm sure you got no class. Now nobody watching class. Okay.